Now we'll discuss about methods of grounding. That is the process of connecting neutral point of three-phase system to earth either directly or through some circuit element is called neutral grounding. Suppose single line to ground fault occurs in line R at point F. This will cause the current to flow through the ground path as shown in the figure. Schematic diagram of grounding you can see here fuse neutral R by B. Note that the current flows from R phase to earth, then to neutral point N and back to R phase. Since the impedance of the current path is low, a large current flows through the path. So this will protect the system from the harmful effects, that is damage of equipment, electric shock of the fault. So the common methods used for grounding neutral point of three-phase system is solid grounding, reactance grounding, resistance grounding, Peterson coil grounding. Soil grounding is usually used in low voltage applications at 600 volts or less. So in solidly grounding system, neutral point is connected to earth. So this reduces the problem of transient over voltage found on the underground system. So however, if the reactance of the generator or transformer is too great, the problem of transient over voltages will not be solved. So here there is the diagram of solid grounding, that is a neutral point of three-phase system is directly connected to earth through a wire of negligible resistance and reactance called solid grounding. Main advantages is lower over voltages, which makes the earth design common at high voltage levels. Disadvantages involves all drawbacks and hazards of high earth fault current, maximum damage and disturbances. So there is no service continuity on the fault feeder. Main applications is distributed neutral conductor, three-phase neutral distribution, and used when short circuit power of the source is low. Next is the resistance earthing. It is used in three-phase industrial applications for many years. It resolves more problems associated with the solidly grounded and ungrounded systems. Reasons for limiting the phase to ground fault current by resistance grounding are: it reduces mechanical stress, reduces electrical shock hazards, reduces the arc blast, it reduces the momentary line voltage dip, it to improve the detection of the earth fault in the power system, and to reduce burning and melting effects in the faulted electric equipment like switchgear, transformers, cables and rotating machines. So this is diagram for resistance grounding. So in order to limit the magnitude of earth fault current, it is common practice to connect the neutral point of the three-phase system to earth through the resistor is called resistance grounding. Next is the grounding resistance, that is connected between ground and the neutral of the transformers to limit the maximum fault current as per Ohm's law to value which will not damage the equipment. And it possible to limit fault currents with the high resistance neutral grounding resistors, and therefore it is most common application to limit single phase fault currents with low resistance neutral grounding resistance. So in addition, limiting fault currents to predetermined maximum values permits the designer to selectively coordinate the operation of protective devices, which minimizes system disruption and allows for quick location of fault. Resistance earthing. Similar to resistance, reactance must be chosen to suit the requirements of protection or to control the inductive interference. The reactive part of the fault current is compensated by this reactor. So the disadvantage of the system is that high transition voltages appear across the system under fault condition. Resistance grounding. Adding inductive reactance from the system neutral point to ground is an easy method. So to limit the reactive part of the fault current in the power system, neutral point reactor can be connected between the transformer neutral and station earthing current. Next is the persistent coil. The current generated by reactance due to an earth fault approximately compensates the capacitive component of single phase earth fault current called as resonant earth system. So a system in which the inductive current is slightly larger than the capacitive earth fault current is overcompensated. However, the experience indicated that inductive reactance to ground resonates with the system shunt capacitance to ground under arcing ground fault, creates very high transient over voltages on the system. Thank you.